An analog to digital converter, or ADC, is a crucial component in electronics that converts continuous analog signals like voltage into a discrete digital form, or numbers, that microcontrollers and other digital systems can understand. This process is essential because most modern electronics, including microcontrollers, only work with digital signals, or numbers. But many real-world signals, such as temperature and light, are analog. The resolution of an ADC refers to the number of distinct values it can output. It is determined by the number of bits used in the conversion. For example, a 12-bit ADC can represent 4096 levels, 2 to the power of 12, while a 10-bit ADC can represent 1024 levels, 2 to the power of 10. A higher resolution means more accurate measurements, which is important when working with sensitive sensors like LM35 temperature sensor, or an LDR, light-dependent resistor, where small changes in voltage need to be detected accurately. In this video, we'll use the ADC to read data from the LM35 and LDR, showing how it helps bridge the gap between analog and digital worlds. Let's dive into how the ADC works and why it is vital in many of today's embedded systems. In this video, we'll dive into interfacing an LM35 temperature sensor with an STM32 microcontroller. We'll learn how to use ADC to read the sensor data and display it on a 60x2 LCD. We will also cover interfacing an LDR, light-dependent sensor, as a sensor, understanding how it generates voltage based on light intensity. Moreover, we have added an exciting functionality. If the light detected by the LDR drops below a predefined threshold, an LED will automatically turn on. Along the way, we'll explore the use of ADC with multiple channels utilizing DMA. Well, let's get started. Launch CubeIDE. Create a new STM32 project. My microcontroller is STM32 F103C826, as you can see here. So I select it. I'm going to call this project ADC LM35 LDR. And we can create our project. The very first thing that I do is enabling the HSE and debug for my microcontroller so I can program it using ST-Link. And I'm going to set the frequency of the system to 16 MHz. Then I'm going to configure the ADC. So I enable channel 8 and channel 9 for ADC1. And as long as I enable it for multiple channels, I set the number of conversions to 2. Great. A scan mode is enabled automatically. I set the external trigger of the ADC to timer 1. Timer 1, capture compare 1 event. I set rank 1 to channel 8 and set the cycles to 71.5 it is going to be connected to LM35, and rank 2 to channel 9 with more cycles because it is connected to LDR. Enable the DMA for ADC1 and set the mode to circular. We're going to read the data straightly from the memory, and we've configured ADC successfully. Now let's configure timer 1, which is trigger of the ADC. Enable channel 1 PWM generation, and we need to set its frequency. As you can see, both APB1 and APB2 clock is 16 MHz. So I set the prescaler to 60,000 minus 1 and the period to 100 minus 1. So the frequency is 10. Don't forget to set the pulse to 100 divided by 2. The duty cycle is set to 50%. Timer 2 is going to create delays in microseconds for us for initializing the LCD. And timer 3 is going to specify the refresh time of our LCD. I'm going to set the refresh time to 1 second. Don't forget to enable its interrupt. Great. Next, we are going to set pins PA1 through PA7 to GPIO output. These pins are going to be connected to LCD. We're going to call PA1 RS because it is going to be connected to RS pin of the LCD. A2 to RW, A3 to enable pin, A4 to D4, A5 to D5, A6 to D6, and A7 to D7. Great. Next, we set PA9 to GPIO output and call it LED. Nice. We are done in CubeMX. So let's generate the code. Now let's add LCD library to our project. To do that, you need to add lcd.zip file to the source section and the .h file to the include section by dragging and dropping the .h file. Great. Don't forget to include the header files of your library to your project. By building the project, you connect the library to your project. Don't forget to replace instances of HTM1 by HTM2 because we've configured timer 2 for the delays in microsecond. And increase the settling time from 15 milliseconds to 100 milliseconds so the MCU have enough time in its initialization phase. If you want to know how to write your own library to interface with LCD, a step-by-step video tutorial link is available in the description below. First, include stdio library to your project in order to be able to use a sprintf function. Nice. Then we need to define some variables here. First is an unsigned 16-bit array of variables called raw value. ADC raw numbers are going to be stored in this array. The next one is an array of unsigned integers 16-bit called ADC voltages. Those raw numbers will be converted into voltage by mathematical implementations and will be stored in this array. And we're going to store the temperature value in this variable. In fact, this is the output voltage of LM35 sensor in degrees of centigrade. And next, we're going to store LDR voltages in this variable called LDR. And next, we define a flag which indicates that 1 second has elapsed. And finally, we create an array of characters called buffer. This array includes 16 characters, and we send strings to LCD with this array. Next, we're going to initialize timer 1 PWM. Nice. Timer 2 will be initialized in its base form. Great. And timer 3 will be initialized in its interrupt mode. This interrupt indicates us that 1 second has elapsed. Timer 2 purpose is to create delays in microsecond, and timer 1 triggers ADC. Great. Next, we are going to initialize the ADC peripheral in the DMA mode. And we store the raw numbers in raw value array. Don't forget to cast it to unsigned 16-bit integers. And of course the length is 2 because we have 2 channels. Great. Now in user code section 4, we are going to define ADC callback routine here. To do that, we need to go to drivers, HAL driver, and find adc.c. Here we are going to find a HAL ADC conversion completed callback function. We copy the function declaration and paste it here. Whenever the conversions are completed, the MCU comes here to implement this function. First, we create a for loop and we convert all ADC raw numbers to voltages by multiplying them by 3300 millivolts, which is the reference voltage, and then divide them by 4095. Why? Because our ADC resolution is 12-bit and 4096 minus 1 equals to 4095. Then we are going to store the temperature value in our variable. According to LM35 datasheet, its output voltage is a linear function of its temperature with the slope of 10 millivolts. So it is enough to divide the voltage of LM35 sensor by 10 and we can understand the temperature in degrees of centigrade. And we store the LDR value in its variable. Great. Next, we're going to define a timer callback routine here, which is implemented every second. Go to team.c file and find HAL team period elapse callback. Copy it and paste it here. Whenever 1 second elapses, the MCU comes here And here we just set the flag to 1 to understand that 1 second has elapsed. Great. Now let's go to our main function, and just before the while loop, let's initialize the LCD, and then with a delay of 100 milliseconds. This number seems to be a good option. Great. First of all, we set a condition here that if 1 second was elapsed and we want to refresh our LCD display, we create a buffer by the use of a sprintf function, and we indicate the warmth of our vicinity by the use of temperature variable, which is produced by LM35 sensor. So we set the cursor to 00 and we sent the buffer to the LCD. In order to show a degree symbol on our LCD, we need to send the decimal number 223 to LCD. So degree symbol will be printed on our LCD. And just after that, we write a capital C, which indicates centigrade. Great. Next, we update our buffer to show the LDR value and voltage. So we use a sprintf function, and we create a string that stores LDR value. We set the cursor to the next row, and we send the buffer as a string to the LCD to print it for us. Great. And finally, we set the flag to 0. Next, we're going to add a condition to our code that if the produced voltage by LDR was less than 1000, which means the vicinity of the sensor is so dark, then we turn our LED on and we set it to 1. Otherwise, if the vicinity of the sensor was not too dark, then we reset the LED to 0 and turn it off. And this is the end of our code for this simple project. Great. Place LCD and the blue pill on your breadboard. Provide 5 volts to the top rail. Provide 3.3 volts and GND to the bottom rail using the STM32 F1 blue pill board. Connect both GNDs together. Provide the power supply for the LCD. It works with 5 volts. Place a 10 kilo ohm potentiometer on the breadboard. Connect the VO pin of the LCD to the middle pin of the potentiometer. Connect one of the side pins to 5 volts. Connect the other side pin to GND. Connect RS, RW, and enable pins of LCD to pins A1, A2, and A3 of the MCU respectively. Connect pins D4, D5, D6, and D7 of the LCD to pins A4, A5, A6, and A7 of the microcontroller respectively. Connect the anode pin of the LCD to 5 volts via a 220 ohm resistor, and connect the cathode pin of the LCD to GND. Place LM35 on the breadboard. provide the GND and VCC pins of the sensor. It works with 5 volts, and connect the middle pin that creates the output voltage to pin B0 of the microcontroller. Place LDR on the breadboard. Connect one of its pins to 3.3 volts and connect the other pin to GND via a 10 kilo ohm resistor and connect it to pin B1 of the microcontroller and connect LED positive pin to pin A9 of the microcontroller via a 100 kilo ohm resistor. This is the final result. Now we can watch the light intensity and the temperature on LCD. If you enjoyed watching this video and find it helpful, don't forget to like this video and subscribe to our YouTube channel. Good luck!